So today we're going to finish our discussion of trees by talking about some advanced trees and finishing some of our operations that we didn't get to on Friday. So we'll finish binary search tree methods with remove, and then we'll look and see how you can use a binary a binary search tree to implement set and map. And then we'll look at the concept of balance for trees, which is really important because that's how we get that O of log n runtime we were talking about. And then we'll talk about some non-binary trees called tries, which are one of my favorite data structures. And then end with some homework tips for homework 6, which comes out today. Okay, so just as a refresher, we talked about binary search trees on Friday. So that's the type of tree where everything on the left is smaller than the root and everything on the right is bigger than the root. So we talked about how to do add and contains, but removing from a BST is a little bit trickier. So, does anybody see how you could maybe remove, this node 4 here without violating the BST property? Any ideas? This one's an easier case. Yeah. Yeah. So in this case, it's really easy because we can just get rid of this node, and then we still have a BST. What if we wanted to get rid of 7? How could we do that? Yeah.
You have to connect 5 to 8.
Yeah, exactly. So it's harder to remove something like 7 because you still have to deal with 7's subtree, right, which is 8. But since there's only one subtree, then you can just replace the 7 with the 8, like you said. Okay, what if we were to try to do something like remove 5? Yeah.
Pull out 5 and have 9 points at 2 now, and have 2 points at 7. So 2 sort of comes to 5. And then
Okay, but what do you do with the 4? That's a good thought. Do you want to try talking with a partner for a couple of minutes to see if I think the idea of okay, let's replace this 5 with a node is really good. So maybe try to figure out which node to replace it with. Okay, does anybody have any ideas? That they want to share? So here, as a refresher, when we had a leaf, we said that one was really easy because we could just get rid of it, right? Then when we had only a left child, what did we replace it with? If we were trying to remove 55, what did we replace 55 with? What'd you say? Yeah, exactly. So when you only have a left child, you can just replace it And then if you only have a right child, you can just replace the node with its right child. So then in this case, we had this concept of replacing with a child, but you can't just like choose 2 or choose 8 to replace with, right? Because you still have to deal with like all of the subtrees of 8 and 2. So does anybody have any ideas of like what might be a good node to replace this with? Yeah.
I'm sure if it's fully generalizable as the right child.
Okay, so you could try to do something like replace 5 with 8. So at that point, we still have like this 6 and 9 to deal with, right? So I think you're on the right track where like we want to replace it with something, but a right child isn't necessarily good because we still have this hard case of what to do with that. Yeah? The rightmost child. What does that mean? 9? 6? So what's special about 6?
It's blue.
Okay, so 6 is blue. Good. Very true. You're definitely on the right track. Yeah?
6, so 5, the reason 8 is to the right of 5 is because 8 is greater than 5.
Mm-hmm.
6 is to the left of 8 because 6 is less than 8. So like if we move 6 into the 5 spot, it would still satisfy having 8 be larger.
Okay, awesome. So the observation is 6 is blue, and 6 is also the smallest element in this subtree. So since it's the smallest element in this subtree, if we were to replace this 5 with 6, we know 6 has to be bigger than everything over here because we know 6 is bigger than 5. And we know that 6 is smaller than everything over here because 6, we just said, was the smallest element in the subtree. Does that make sense? So the reason this is a good thing is because what do we notice about 6? Does 6 have both a left and right child? Yeah. Yeah, so the smallest element in the subtree is only going to have a right child because if it had a left child, then that left child would be smaller than the like the smallest element, which is bad. Yeah?
Why wouldn't we use 4?
Okay, so the question is, why wouldn't we use 4? You could use 4, so you can either use the biggest element from the left subtree or the smallest element from the right subtree. I chose one. Yeah, but either implementation is totally valid. So the nice thing about using 6 is this is an easy case that we just talked about, right, in the previous slide, where we could just directly do this substitution. Okay. Are people kind of feeling okay about this? Binary search tree remove is by far the hardest binary search tree operation. Okay, so yeah. So we need to find the smallest element of the subtree. Do we have a way to do that? Does anybody remember from Friday? One of the methods we wrote? Nope, nobody's here on Friday. That was like a week ago. Okay. Hold on. Don't know why my QT creator. Interesting. Okay. So we wrote print size contains height, add, get min, get max, and then we're working on remove. Any of those sound like a method we could use? Yes, get min. Okay. So, okay. Okay, so in order to, so we said there were 4 cases, right? But in order to even get to those 4 cases, we first have to find the element that we want to remove. Does anybody kind of remember like that formula we were doing with binary search trees? Like how do we get to that element that we want to remove? So if the data is smaller than the value, what do we want to do? Yes, so, okay. So if the value we're looking for is bigger than the value we're currently at, which way do we want to go, left or right? You think you're on the right track? Yeah, you go right. So because everything at the right of the root is bigger than the root. And the value we're looking for is bigger than the root. So, okay? We'd say remove node right. Else if node data is greater than value, we go left. Okay? So we have our 4 cases, right? Left subtree, right subtree, case 4, full tree. So, okay, so what do we want to do if it's a leaf? Yeah, so we can just say, okay, let's set this node to the null pointer, right? So one thing about this is what happened to that node, that struct that was there in memory. Does it still exist?
Yes.
Yeah. So what do we have to do about that?
Delete it.
Yes. Okay, so we can call delete node, and then node equals null pointer. Okay. So what about this case? Where we only have the left subtree. Yeah.
When you delete the node, you don't have to you not have to create like a temporary node.
So the question is, when we delete this node, do we have to create a temporary value? In this case, we don't, because we aren't doing anything with that node. Like we don't need to get any information from that node or anything like that. But we will see other examples where we do need to kind of do some sort of temp. Yeah?
Can you make the text bigger? Like zoom in?
Yes.
What do you think?
Can you see that?
Yeah.
Okay. Can you see that in the back? Right there? Okay. Cool. So, yeah. So the question is, why are we deleting this node and saying it equal to the null pointer? Like, I thought you all said that you didn't need to do that. Okay, so what happens is when we remove the node, we definitely need to delete it because we don't want that node to exist anymore. But you also need to set its parent, like the parent pointer to that node equal to null. Right, because you don't want that parent pointer to continue pointing down to like memory that is no longer, like that's now garbage. So in this case, you have to do both. Does that kind of make sense? Yeah. It's kind of like with add, how we had to like set the node equal to some new node. It's the opposite of that, basically. Cool. Okay. So what about when you have, or are there any other questions about like this case and what we're doing in this case? Yeah.
So, sorry, just to clarify, when you delete node, are you deleting, you're not deleting the node itself, you're deleting what it points to?
Right. So the question is, when you delete node, what's actually happening? So doing is we created this, so this is actually like this has a right and the left. Right, so node is this right pointer, and this is the thing that's actually in memory. Right, so when we call delete, it gets rid of this, but like you can't delete this pointer. This is just an address, right? It's kind of analogous to you can bulldoze a building, but you can't like obliterate an address, right? That address will continue existing. So that's what's going on here. We're bulldozing the building. The address will continue existing. Great question. And then we also said equal to null because this, like right now, this still has an address, right? Is this block of memory? So like this memory is now garbage. It's just the rubble left behind after bulldozing the building. So if you cultivate a move there, they'd be really upset. So you instead would now make this equal to null. That's the two parts that we're doing. These are really good questions. Okay. Sorry, people on the video. Come to class. Okay. So, how are people feeling just about this portion? Okay. Seeing some thumbs up. Yeah.
Since the node is passed in by value instead of by reference, what's going to happen when you set it to null?
Great question. So the question is, since the node is passed in by value instead by reference, when you set equal to null, doesn't that not change anything? Good observation. So what should we do? Pass by reference. Yep, and so in general, anytime you're modifying like any sort of linked data structure, like a linked list or a tree, passing it by reference is the best bet, which is what we saw with the add on Friday. Great observation. Yeah?
When you are facing something that only has one child, are you ever going to be in a situation, and let's say it's on the left-hand side, you're ever going to be in a situation where like the child is greater than what was on the right, and then you need to switch them, or
So you're asking like, okay, let's undelete this node. If we were to delete like this node, there's like 4s up here. So if we were trying to delete this node, is there ever a situation where like when we're replacing it with the 6, that we would need to like switch it to the other side of the tree? Is that your question?
what if say the 6.5 didn't exist?
Okay.
So if you have one child, but then they, no, I can't answer my answer. If you ever have to replace it back up, like would you ever have to think, say, if you had to fix it, it would be ever smaller than the 2, for instance, and you'd have to then have an issue with this.
Okay, I think the simplest answer is that everything on like the right of the root is guaranteed to be bigger than it, and everything on the left is guaranteed to be smaller. And this is true going down the tree, so you can't really get into any situations where you're like moving, like as long as the subtrees stay the same, or like as long as you aren't switching which subtree the node is in, you'll still be okay. Does that make sense?
Yeah.
Okay. Okay. These are really good questions. Okay, so when we had the right node was this is a null pointer. So we only have a left subtree. What did we want to do? As a hint. Here we go. That was this case. Like we wanted to replace it with the left child. But how can we do that? Like we're gonna have something like node equals node left, right? But is that all we need to do, or is there anything else?
need to create like a temporary node to hold what we want to delete.
Yeah, exactly. So we need to create a temporary variable. So this is going back to your question about whether we need a trash variable. And in this case, we do because we need to get information from that node that we're deleting. Okay, and then we would delete trash. Node left, and then we do the opposite with the right case. So what questions do you have about these two cases? Yeah?
So we needed to clear trash low pointer.
So the question is, do we need to declare trash to be null pointer? So in the case where we were just deleting the leaf node, you would want the parent to be pointing to null, right? So that would be like this case, right? We wouldn't want 29 to continue pointing to anything, so we would make, or on the left side, so we'd make 29 point to null on the left. But in this case, we actually want, like if we were to replace 29 with, or if we were to delete 29, we would want to replace 29 with 42. If we were to make 55 point to null instead, then you would end up with, like you would lose this 42, that whole subtree from your tree. So that's why we aren't doing null pointer. In this case, we're setting it equal. We're now, instead of setting it to null, we're setting it equal to the right child or to the left child. Does that make sense? Okay. Somebody else have a question back there? Okay. Yeah. Sorry, how do we have Yeah. Okay, so the question is, why do we have this trash pointer? So let's say we didn't have this, right? So in this case, we could choose to delete node. Like if we were to delete node here, you can't do anything with node left because node left doesn't exist anymore. It's just rubble, right? Or if we were to like delete node here, now you're deleting node after it's been like reassigned to the new value. So in that case, like it'd be the equivalent of deleting 42 instead of deleting 29. Great question. Okay. You ready to tackle the really hard case? Okay. So in this case, which function do we have to use again? Yep. So get min of node. Okay. So then we said we wanted to replace the value in the node we're deleting with the minimum value, right? So we don't need to like rearrange the tree, we just want to replace that node. So we can do that by saying node data equals min value. Oops. And then, right? Is this kind of making sense? So this would be, we have this 5 and we want to replace it with 6. So we can just copy the data of 6 into the node 5. So we now have a 6 here instead of a 5. Yeah. Right. So what do we want here instead of get min of node? Right. Yep. Get min of node right. So that this way you're now getting the minimum of this subtree instead of the minimum of the whole tree. Okay. So, okay. Like that's great. We now have a 6 here. What else do we need to do? There's another 6 down here still, right? So what do we need to do with that node 6? Somebody say base case? Actually, it's like kind of the opposite of base case, which would be, like, could we maybe use this remove function at all? Yeah.
Yeah, just call remove again.
Yeah, exactly. So we want to call remove on what node, left or right, or the node itself?
Same tree, so it would be the same direction as the one before.
Yeah, so we'd want to do node right, because if we were to call remove on the node itself, we're going to end up removing that node that we just changed, right? So that's not good. So okay, so we call remove on node right, and we look for a min value. So basically what this code is doing is it's like, okay, let's find that minimum value, like that 6. Let's replace the 5 node with a 6 instead of with the 5. And then let's remove 6 from our tree. But this is actually approaching the base case because we know that that case is going to be somewhere up here, which are the easier cases. Yeah.
So if you enter in a min value to this function as it is, what happens if that value doesn't already exist in your tree? Like, are we assuming that the value is in there?
The minimum value?
Yeah.
Okay, so the question is like, what if minimum value doesn't exist in your tree? Getmin has to return a value that's in your tree. Like, assuming our code was correct on Friday, Getmin will return a value that's in your tree. Great question. So like, yeah, so it's guaranteed to be in the tree, so this will all kind of work out. Cool. Yeah.
So the first thing we did, like our first 2 if statements, were to try and find the node that has the value that we're trying to remove.
Yeah, okay. So the question is like, what are these first 2 if statements? This is the part where like your canonical BST code where you're just going left and going right to find the node that you want to do something with. So yeah, this is just like looking for that node to remove. Then we finally find it down here, and then we have those 4 cases that we talked about. So case 1 was the leaf, where we just like set the parent equal to the null pointer. And then case 2 is where we could just replace it with its child. And then the 4th case was the full tree, right, where we needed to go find that minimum value and then replace the node with the minimum value and then delete the minimum value from the tree. So the good news is that this is as hard as BSTs get, really. Like if you got this, you've like nailed BSTs. What other questions are there about this? Cool. So we spent a lot of time talking about BSTs. You're probably like, why are we doing this? So this is how basically how the Stanford set and Stanford map are implemented, which is why when you're iterating through your set, you'd get an order to it, right? Unlike the hash set, which just had the random values, it's because BSTs are ordered. And then that's also why you have the log n time to search, add, and remove elements, is because binary search trees have O of log n time. So we've just written add, contains, and remove, which required a, basically, we might have like this tree set, which would have these add, contains, and remove methods, but they wouldn't take in a root because your binaries, your set should just have the root, right? Like when you've been using the Stanford set, you don't have to be like, oh, and here's my tree node root that I'm passing in. You don't have to keep track of all of that. The set is keeping track of that, right? So a really common thing is you would have, something like this, where this is what you as the client would call, you as the person using the set or the map. And then this function would just call like some helper, which is the code that we wrote in class on Friday and today, and it would just pass in the root as that node. Does that kind of make sense? Yeah, so the good news is, yeah.
So, are we assuming that you're constructing a root within the first function based on those parameters and then passing that in?
Yes, the question is, are we assuming we're constructing a root based on the parameters? So it's more that the root is just a member of the class. So before, what was happening was in the main method, in like down here, I just had a root, right, that I was keeping track of in the main method, and I was calling add on this root. But you can imagine you would have like this tree set, which then is keeping track of the root itself, so that the client doesn't need to do what I did down here. Yeah.
But when you only have access to that root, why would we have calls with it?
Yes, the question is like, why do we need to keep? Why can't the client just keep track of the root? So can you imagine if on week 1 we're like, okay, so we're learning about sets and maps, and so there's this thing called like a tree node star. You need to set this equal to null pointer originally, and then like you need to pass this in, like, but don't worry, like this data structure is really good for contains. You'd all be like, yeah, I'm using a vector forever, right? So that's why, so you kind of want to like. A lot of times in computer science, you want to hide some of the implementation details from the user. So in this case, you want to hide like the fact that it's actually a binary search tree. The user doesn't really care. It just wants the code. It wants the data structure to work in the time bounds that we're guaranteed, right? Great question. Okay. So, okay, this works great for sets, but maps have keys and values. So you can kind of imagine you aren't going to have like that single struct that just has like the one value, right? You would now store key and a value, and these can be whatever types you want. And then the important thing is that you have a tree that is binary. It's ordered by the keys. It's not ordered by the values. That's why it's really fast to do like a get on the key, and you can only have like one key, but unique keys, but you can have like multiples of the same value. That sort of thing is because you have this binary search tree on the keys. So you basically just have like a set of keys, and each key has a value associated with it. One of the other tricky things about both sets and maps is that you have to implement this less than sign, which I don't know if any of you tried to create like your own struct for Boggle, but if you did and ran into weird issues, it was probably because of this. Cool. Great. What questions do you have about like how the Stanford set and map are implemented? Yeah.
For the key lock,
Key lock.
yeah, isn't that one, should the key connect to the jack?
Okay, so the question is, shouldn't lock be connected to jack? So these are ordered by string, so it'd be J, K, L. So J is less than K, but L is greater than K. So that's why L is in this subtree and J is in this subtree. Yeah. And as you can see, like the values are basically just random. There's no ordering on the values. Which is why it's really hard to write like a contains value function, but it's really easy to write contains key. So basically, all of those methods that we just wrote have an analogous method in map. So you have put for add, contains key for contains, and remove for remove. The other big change is that you would have to write like a get method to get the value associated with the key. But that's pretty similar to contains. Instead of returning true or false, you would return like the actual value associated with it. Okay. So I know I just said that the Stanford library basically uses a binary search tree. It actually slightly modifies it. And the reason is that it's not a plain binary search tree. It's modified to have something called balance. So the reason this is important is because when you have unbalanced binary search trees, you lose the log n runtime. So like, for example, what would the binary search tree look like if you inserted the elements in this order? Like 5, then 1, then 2, then 4, then 3. Yeah?
All of the outputs side would be the root, and all the elements would be the left.
Yeah. So you end up with this, like, it looks like this, where you end up with this line, basically, of elements. So instead of having, a nice looking tree that every level is basically like half of the elements are on one side and the other half are on the other, you get like a line. So if you have this line, what is the runtime of doing something like contains on this tree? Yeah, O of n. You just made yourself like a really fancy linked list. So that's not good. So in order to try to prevent something like this, and this is somewhat of an extreme case, though you can imagine if you had like 1,000 nodes being off by like even, you might have, 10 in one subtree and 990 in the other, and that would still be really bad. So it doesn't necessarily need to be like a straight line for you to still have like really bad runtimes. So basically a balanced tree is one where you just make sure that the subtrees are essentially the same size or very close to being the same size. And so our Stanford libraries actually have that guarantee built in, and there are some like modifications that you can do to make sure that you get a balanced tree. So one example of something you can do is something called a red-black tree. You'll learn more about these if you want to continue into computer science. Nobody codes red-black trees. You don't need to know how to code a red-black tree for like this class, but basically the idea is you do something called a tree rotation to like maintain balance, and there's like you have this like node coloring to ensure that there are only so many nodes in one subtree versus another subtree. It's kind of complicated. If you're interested, you can look it up more, but the Stanford library would implement something like this. Okay. Brief timeout for announcements. Exam scores have been released on Gradescope. So if you haven't made a Gradescope account before, you can do that just by going to Gradescope. The course entry code, if you're asked for it, is posted on Piazza. You can also see our website for statistics and regrade information. Some of you might not have done as well as you want, but there are still a lot of opportunities to get points this quarter. Like this midterm does not in any way indicate like your aptitude for computer science. So it's one exam that we have to do. And there's still a lot of opportunity left in the quarter to get a grade, whatever grade you would like. Cool. And then the other big thing is because Marty isn't going to be on campus as much, Amy and I have both expanded our office hours, which you can see if you go to the staff page on the website. Great. Okay, so I promised you I'd talk about tries, which is my favorite data structure. So the way tries work, we've been talking a lot about binary trees. We have like a left child and a right child. So, did somebody say something? Okay. So you have a left child and a right child, but the logical question is like, why are we doing this? Couldn't we have like as many children as we want? And tries are like, yes we can. So the way a try works is each node is basically storing it's used for storing strings. This is how the Stanford lexicon is implemented. And so each node has 26 children pointers, one for each letter in the alphabet. If you were doing a lexicon for some other language, you might have more or fewer pointers depending on the size of that alphabet. And so basically, you would if you follow, the A pointer and then the T pointer and then the E pointer, you would spell out the word 8. And so the idea is when you follow those pointers going down the try, you end up with at a node, and if that node has this is word is true, then you're at a word, and if it doesn't, then you aren't at a word. But like the nice thing is if it doesn't have is word is true, but it like you are still at a node in your trie, that means that you are at a prefix for a word, right? So like you can imagine like OU is not a word, but OUT is. So the only reason you can still be at a node for OU is because like you're eventually going to build some word if you follow the correct pointers. So as like a clearer example, I omitted all the null pointers because otherwise there would be 20 like arrays of size 26, which gets very difficult to follow. But you can imagine there are actually like 23 null pointers in this array as well. So if you were trying to see like, okay, is the word ATE in our trie, we would start off here and be like, okay, the first letter is A, so I'm going to go down the A pointer. The next letter is T, so I'm going to go down the T pointer. The next letter is E, so I'm going to go down the E pointer. And look, it says word is true, so therefore we are at a word in our trie. If we were trying to see if like once is a word in our lexicon, we would go, okay, O and then N, and then there C is null, so we'd say, okay, once is not a word in our trie. What questions do you have about tries? Yeah.
We have two valid words like on and
Yep.
how would we be able to like know that was still valid?
So the question is, if we have like one and on, how do we know that on is a valid word? Because like couldn't on just be a prefix for one? So that's why we have this like is word field, is because like when you get to on, it'll say like true or false, am I a word? Because like English and other languages do have words that are prefixes of other words. So you just have like a Boolean flag for if you are a word or not. Great question. Yeah.
So by definition, all the leaves in the trie are words.
Yeah, so the question is, by definition, all the leaves in the trie are words, and yes, that is true. What other questions do you have? Okay. Yeah, so we don't quite have time to write contains prefix because I did want to talk about Huffman. But essentially the idea is, okay, if you ever hit a null node, you are not a prefix because you've fallen off your trie. And then if you run out of letters in your word, you've like followed something down, you're still at a node in your trie, then you are a word. And then otherwise, you want to get the next character, you subtract out the ASCII letter or the ASCII value for A to figure out like which of the pointers to go to, and then you recurse going down that child. So the big difference is instead of having left and right, you have this like array of pointers. As a hint, you might use something like this for Huffman, which is homework 6, where you'll need to convert between characters and numbers, right? So instead of subtracting the value for A, you might want to subtract the value for 0. Okay. What questions do you have? Any last questions about tries? Or do you want to move on to Huffman? Okay. So homework 6 comes out today, and essentially what you're doing is you're writing a compression scheme to like make files smaller. So ASCII has 1 byte per character, right, no matter what. So A has the same number of like takes up the same amount of space as like weird punctuation that nobody ever uses. And so what we want to do instead is we want to do some like variable length, where you would get like spaces and A's are shorter than 1 byte, right? These are only 4 bits instead of 8. But you get something like Z might be longer. But that's okay because we use fewer Z's than we do A's. So overall, if you have a large enough file, your file will still be smaller. So the idea is we're going to be creating a tree where you have, instead of having a left and a right pointer, you have a 0 and a 1 pointer. And so left means go towards 0 and right means a 1. And then the idea is, like, if you're higher up in your tree, then you're going to have a shorter binary value, which is nice because then you're, like, that's how the compression works, right? So in order to do this, there are basically a bunch of steps that are outlined on the handout, but you need to count the occurrences of each character in the file. So, like, read the file character by character, and then place the characters and counts into a priority queue. So something that you just wrote is coming back in this assignment. And then you want to use the priority queue to create a Huffman tree, and then traverse the tree to find the character to binary map. So the way that we traverse this tree is kind of similar to how we were traversing a trie, where you're going to be building up this string based on which pointers you go towards. And then for each character in the file, you would then convert it to the compressed binary version. So it basically, when you're building this up, you want to know, like, when you go left, you want to, like, keep track of the fact that you just traveled down a 0. And when you go right, you want to keep track of the fact that you just traveled down a 1. And you'll be building your string up that way. And then when you decompress, you'll need to, like, start off somewhere and then, like, choose whether to go left or right, depending on if you've read a 1 or a 0. One thing that's good to note about Huffman is that you will never have a prefix that's, like, a valid encoding for a character, right? So you can't, like, be in the middle of your tree and end up with a, like, it's not like, oh, well, do I stop here and output this character, or do I keep going? Like, all the valid characters are leaf nodes. And there's some input and output stuff with this assignment. So you'll be using bit streams, which input and output individual bits instead of full characters, because, again, the point of this assignment is to, like, compress the file. So you need to be working at bit level instead of at a character level. Any questions about Huffman? You excited?
Excited.
Yeah, okay. Great, and see you all on Friday.